Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 17th episode in a series that seeks to demystify programming in assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel. Don't forget to subscribe and click the bell for notifications while you're there so that you know when the next episodes come out, and start this playlist from the beginning. So far in this series, we have learned the fundamentals of assembly programming by going through the entire 65C02 instruction set and examining how each instruction works, and since then getting into specific capabilities of the X16. We have already seen how to generate sound using the Vera programmable sound generator, but that is only one of 3 options that are available for the X16. And while it is easy to interface with, it is very limited in terms of what kinds of sounds it can make. You can do proper frequency modulation synthesis with the Yamaha YM2151, which is included right on the motherboard. You can define sophisticated instruments and play pitch-perfect music. However, there is a much steeper learning curve for using it, as it is effectively a full-featured synthesizer on a chip, and its features are complex. In this video, I will also be using a lot of musical terminology on top of all the synthesis concepts. I'm trying to make this as simple as possible to understand, but this is definitely something that one could spend a long time studying to gain expertise, which I freely admit I do not have. I am going to go through enough to show you how to incorporate using this chip in assembly code and giving you a jumping off point for exploring all of its features. Another name for the YM2151 is OPM, or FM Operator Type M, to differentiate it from other Yamaha synthesizers on a chip. But the OPM has the distinction of being the very first one. It is also fully an 8-bit chip, so it works nicely with the 65C02. It provides 8 independent stereo voice channels, each of which can be configured using 4 FM functions. One channel can also use a built-in noise generator. The voices can play any chromatic note in an 8-octave range, either perfectly or with a configurable fraction of sharpness. Yamaha originally created this chip in 1987 as a central component of professional keyboard synthesizers, starting with the DX21. They continued to use it in other keyboards, eventually including some consumer-grade keyboards for casual use. However, its most prominent use, at least in Western markets, was in arcade cabinets, starting with Atari's Marble Madness. Many other cabinets followed, including quite a few from Sega, which included the OPM along with their own PCM audio hardware to combine synthesized instruments with drum samples and other effects. While its cousin, the YM3812, or OPL2, found widespread use in the PC market thanks to the AdLib and Sound Blaster expansion cards, the OPM was mainly used only in Japanese computers like the Sharp X68000 that were not widely used outside of Asia. But many chips were made, and enough are cheaply available to be viably included with the X16. The OPM interface, in a logistical sense at least, is very simple. The hardware interface is only mapped to 2 memory bytes for all of its I/O with the CPU. The only read supported is the write-ready signal, which you can see by loading the value at hex 9FE1 and checking the state of the highest bit. Once it's clear, the chip is ready for you to write a new register value. First, you write the register address, specified by the map you see here, to hex 9FE0. Every address that isn't completely X'd out is something you can write to. With the register address set, you then write the register value to hex 9FE1. This will result in the contents of that register being updated on the chip, and the sound output could change depending on the other register values. You can only read the write-ready status. All of the registers are strictly write-only. The most complicated part of programming the OPM is defining instruments, which is done through configuration patches that can be written at any time. This means that a voice channel can change instruments on the fly, but that generally comes at the cost of requiring more memory to store your music track. A patch consists of config values for each of the 4 FM functions, consisting of 6 register values for each of them. This means that each voice is defined by 24 of the registers you see on the range pictured to the right. We aren't going to go into what each of these are for, except for the simplest one, which is TL, or total level. The TL registers let you set the level of each function for each channel, with a value of 127 for maximum loudness. On top of configuring each of the 4 functions, there are also a few channel-wide settings in its control registers, including whether to output to the left and/or right speakers, what the feedback level is going to be, and how the functions are connected. There are 8 different ways that the functions can be connected, letting you select different combinations of parallel or serial wave processing. Again, this is deeply technical and not my area of expertise, but you can definitely play around with all of these settings and see what different kinds of sounds you can make. You can come up with an extremely diverse sound palette. Once your instrument patches are set, it's much easier to simply play a note on a channel. There is a single register at address 8 called KEYON, or KON for short, that controls which functions are currently playing on the specified channel. Bits 6 through 3 set the enabled functions, and bits 2 through 0 specify the channel. So if you only write the channel number to address 8, it will cause that channel to go silent, which is called key off. Generally, you will have all 4 functions enabled when you want a key on to happen, but you may have a patch that creates purposely different sounds based on the enabled functions. Before you enable those functions, however, you'll need to set the key code, or KC register, for the channel. These are at addresses hex 28 through 2F, with 1 for each channel to set both the octave in the upper nibble and the note itself in the lower nibble. The note can be anything on the chromatic scale from C sharp up to C, but the values are a bit odd. The notes are in groups of 3, with undefined in-between values at 3, 7, 11, and 15. If you did actually want to play an in-between note that's not on the chromatic scale, you'll want to use the key fraction, or KF register, in the address range hex 30 through 37. To have your notes right on pitch, this should be set to 0, but you can increase the pitch in increments of about 1.6 cents by setting the upper 6 bits to a value up to 63. For some reason, the lower 2 bits are unused, so you can get a 50-cent sharpness by setting the fraction to 32, which after shifting to the left by 2 bits means writing a value of 128 to the KF register. So you can do a very smooth portamento between notes, but it will require a lot of register writes over a short period, and that can also really drive up the memory requirements of your track. Let's go through a simple case study to see how to play a repeating note. We're going to assume that channel 2, identified by index 1, has the desired patch already configured, and that the only expected interrupts are coming from the video vertical sync, which happens 60 times a second. We're going to define a subroutine that will play middle C on channel 2 for half a second, then rest for half a second, then repeat for 10 total notes over 10 seconds, and after that it returns. This isn't a really efficient use of resources, but it will help to illustrate how you have to time OPM register writes. First, in the black code, we define some constants we'll need. The memory-mapped YM2151 register address and data channels are first, followed by values we need to write to them. There's the KON register for doing key on and key off events, followed by a bit mask for enabling all 4 FM functions, and the index for channel 2 to write to KON. Then there's the KC register address and the value we write to that to specify middle C. In the following red code, we label our subroutine ostinato, as that's what it will produce. We start by making sure the channel 2 key is off, by not setting any of the function enable bits in KON, only the index for channel 2. So we write the address of KON to YMReg, followed by the channel 2 index to YMData, which triggers the write to the OPM chip. Then in the blue code, we set the key code to middle C by ORing the channel 2 index with the KC register base address and writing that to YMReg. Then we write the constant we already defined for middle C to YMData, and we're ready to start playing the note. In the following gold code, we initialize our loop by loading 10 into X and start each iteration by checking if the OPM chip is ready for a new write. If we read the high bit of YMData as being set, then it's not ready, and we branch back to the top of the loop. Once it goes clear, we continue on to the green code, where we set a new value to the KON register. We want all FM functions enabled, so we let the assembler OR the all-on bit mask with the channel 2 index together and write that to the chip. Then we start our first delay loop in the following red code, using y for this loop index and waiting for 30 interrupts to go by, which should take almost half a second. Once y gets down to 0, we're done waiting and ready to stop playing the note. We follow the blue code and write only the channel 2 index to KON, leaving all the functions disabled, generating a key off event. Then we do another half-second delay loop in the following gold code and follow to the green code where y gets down to 0 again. We finally get to the end of the cycle loop, so we decrement x and keep going until we go through the whole on-off cycle 10 times and x gets down to 0 and we return. The OPM noise generator works through the C2 function for channel 8, so we can enable that function by writing hex 47 to the KON register, which will start playing the noise, and then writing just 7 to KON will stop it. But first, we need to enable the noise generator and set the dominant frequency by writing to the noise register at the hex address 0F. Bit 7 is used to enable the noise generator. When it's clear, channel 8 will have use of the C2 function to do FM synthesis, as defined by the current patch. But when it's set, the C2 patch is ignored, and channel 8 will generate noise when C2 is enabled. The lowest 5 bits of the noise register are used to define the dominant frequency, using the formula of the OPM clock frequency divided by 32 times that value. This means that the output frequency is indirectly proportional to the frequency value, ranging from 3.5 kHz for a value of 31 to 111.9 kHz for a value of 1. As it would imply a divide by 0, a 0 value is not valid for noise frequency. While this noise generator can be easily introduced to OPM music tracks, if you want to just generate some noise, the Vera PSG noise generator may be a better option, with the ability to generate more than one noise channel at a time, a wider range of frequencies, and a much simpler programming interface. For our example program, we're going to create a simple music player, and to test it, we will define a track for Mozart's Eine kleine Nachtmusik, which for those of you whose cultural awareness doesn't go beyond video games, it's the theme music for the original Mario Brothers arcade game. We'll use an arrangement that has 4 piano voices and 4 string voices, and set up the patches for those instruments before the track plays. For an extra example, I'll demo the title sequence for my upcoming game Cavi's Quest, which is written using the XCI game engine and its software development kit that can convert VGM files into OPM tracks that can be loaded and played by the X16 using the engine. But first, let's get to the code of our simple music player. We start with the standard section preamble and jump start, but then instead of defining all of the standard X16 constants we need, we simply import x16.inc, which will define all the memory locations we need, including the YM2151 register address and data channels. Then we include ym2151.inc to get all the register addresses and values we will need. Both of these files are used in several of my projects, including the XCI game engine, and are handy to use for any X16 assembly project. Reusing include files like this is also an easy way to deal with system changes, which are bound to happen while the X16 is still in development. Just update one file, then copy the changes to all your projects. Moving on, we still need a constant for the vsync bit that is used by the Vera IEN and ISR registers. Then we want to place our patches in memory. We have those defined in a separate file named patches.asm, so we include them here in between a pair of labels so that we can have the addresses where the patches start and end. Then we have some more constants, including a 0-page pointer for going through music data, and the number of vsync ticks that will comprise half a beat. Our track is going to be using an 1/8 note resolution for simplicity, so we only have to have key events happen twice per beat. By making half a beat take 15 ticks, we'll have an effective tempo of 120 beats per minute, which is a good fit for the light Mozart piece we are going to play. The track we are going to define will need to have a way to indicate when these half-beat boundaries are going to be. But there's no OPM register for a simple delay, so we need to use an undefined register address to indicate a wait, so we can use 2 for that. Then we wrap that into a macro called wait half beat, where we allocate 2 bytes, starting with the wait reg value we defined, then a 0 as we don't need any data, but we still need to take up the space for consistency. Then we create another macro to mark the end of the track, using 4 for the register address, as that is also unused by the chip. Again, we just use 0 for the data value, and we can just place end music at the end of our music track. For actual notes, we define a macro that will define the 3 address value pairs that we need to write for any note, as defined by the channel it will play on, the note key, and its octave. We can use constants from ym2151.inc for all these values, and that will allow us to define our track without hard-coding any numbers. To play the note, we'll want to disable all the functions for the channel by writing only the channel index to the key on register. Then set the key code register for the channel with the note key and octave. Finally, we write the channel with all 4 functions enabled to the key on register and start playing the note. Now, each time we instantiate the note macro, it will allocate 6 bytes using the passed arguments. We define one more macro called rest that will simply allocate an address value pair to write only a channel index to the key on register, which will indicate the beginning of a rest for that channel. Now we can build a full track by combining these 4 macros, which we do in an external file called eknm.asm, which we include in between another pair of labels. Now we need to define some global variables that we'll be using in our custom IRQ handler, including the address of the default handler, a counter to tick down as we wait for the next half beat, then a flag to indicate we are done playing the track. At start, we begin by writing the patches to the OPM. So first we need to initialize our music pointer, which we'll use first for iterating through the patch data. We store 0 to the low byte of music pointer, and then load Y with the actual low byte of the start patch's address, as we will be using the indirect index with Y mode to get the data. Then we put the high byte of the address into the high byte of music pointer, which we can now just increment whenever Y rolls over to 0. We start the patch loop iteration by waiting for the OPM to be ready for a new register write, which will happen once the high bit of YM data is clear. Then we load the next byte for the patches, which we will expect to be an OPM register address. We go ahead and store that to ymreg, then increment Y to get to the value we are going to write. But first we check to see if Y has rolled over to 0. If it hasn't, we branch ahead to @WriteData. Otherwise, increment the high byte of music pointer and continue on to @WriteData. There, we load the value and write that to YM data. Then we increment Y again to get to the next address. Again, we check to see if Y rolled over and increment the music pointer page if it happens here. Then we check to see if we are on the last page of patches, and if we aren't there yet, we just branch back to the top of the loop. Otherwise, we need to check to see if Y is up to the low byte of end patches. If it is, then we are done writing the patches and we fall out of the loop. Now we're ready to start playing the track, so we set music pointer to the start music address. Then we initialize the rest of the global variables by clearing the done flag and initializing the counter to 1 so that the track starts playing as soon as possible. As we've done many times before, we back up the default IRQ handler address and replace it with the address of our custom IRQ handler, while we also make sure that only the vsync interrupts are generated by the Vera. In our main loop, we wait for the next interrupt, then check the done flag. While it's still clear, we keep looping until the high bit is set and we fall out. Then we restore the IRQ vector and return to basic. In our custom IRQ handler, first we check to see if this is a vsync interrupt. If it's not, we branch ahead to @continue. Otherwise, we write the ISR value back to reset the latch and then decrement the tick counter. If it's not down to 0 yet, we branch ahead to @continue. Once it does get down to 0, we fall to the music loop, which we start by checking if the OPM is ready for a register write. Once it is, we load the next register address from music pointer and check to see if it's the special wait register address we defined earlier. If it is, we branch ahead to @wait. Otherwise, we check to see if it's the end register we defined, and if it's that, we branch ahead to @endMusic. If it's neither of those, then it's a real register address, so we write it to ymreg. Then we load 1 into Y to get the register value with indexing. Then we store that to YM data and unconditionally branch ahead to @next. If we saw a wait register address, then we would have branched to @wait, where we load 0 into Y, then continue to @next, where we add 2 to music pointer. Then we check if Y is 0, and if it's not, we haven't reached a wait yet, so we go back to the top of the loop to keep iterating through the track. Otherwise, Y was 0, indicating that we're done, So we reset the counter to a half beat's worth of ticks and unconditionally branch ahead to at continue. If we came to the end of the track, indicated by the end register address, we would have branched to at end music, where we call the stop all subroutine and make sure all the channels are silenced. Then we set the done flag so that the main loop can end, and that will be the last time this custom IRQ handler is called. Then we finally get to at continue, where we simply jump to the default IRQ handler and let it do its processing before returning from the interrupt. Finally, the stop all subroutine instantiates a macro called ymsetReg, passing in the key on register address and each channel index. Then we return, and we're done with this code. Before we try building this, let's take a look at the files we included, starting with x16.inc. Here you can see we start with a .ifnotdef control command, which works just like a #ifnotdef in C. This is good practice for include files in assembly, just like it is in C, as a lot is going to be added to the namespace, and we don't want to accidentally include it twice. So we only include the contents if the x16inc constant isn't already defined. And if it isn't, the first thing we do is define it, giving it the arbitrary value of 1. It doesn't matter what you actually set it to, just as long as you define it. Then we do the same thing for another constant called cx16 that's surrounded by 2 pairs of underscores. This is added for compatibility with include files that come with CC65, effectively forcing the target platform to be the commander x16 if it wasn't specified on the command line. We're not using that here, but it's nice to have as a failsafe. Then we get into all the constants we need for the x16, including the 16-bit ABI 0-page registers, Vera registers, memory banks, kernel subroutines, more kernel subroutines, vector locations, and finally some macros for common activities. Then we have ym2151.inc. Here we have the same .ifnotdef command, but with a new unique constant. Then we go ahead and include x16.inc here, as it is a dependency. Since we did the ifnotdef thing there, it's perfectly safe to include it here, even if it was already included by the source file that included this one. Then we have the ymsetReg macro that we saw earlier. It takes 2 arguments, a register address and a value to write to it. We first wait for the OPM chip to be ready, and we use an unnamed label for branching back until the high bit is clear. Then we go ahead and write the register address to ymreg, and then the register value to ymdata, and that's it. For cases like silencing all the channels at once, it makes that code much cleaner and faster, if a bit inefficient space-wise. Then we have all the register addresses and data constants, including some helpful data field combinations to simplify your code. So these 2 include files are nice to have for any x16 application, especially if you're using the ym2151. Let's take a look now at the data files we included, starting with patches.asm. As we saw in the code, the patch data needs to be pairs of register addresses and data values that will be written out as quickly as possible. This may take a long time as you're waiting for the OPM chip to be ready for each register write, but once these patches are set, they don't need to be changed for the rest of our program. But in other cases, you may want to change patches on the fly, and that will require more memory to store these transitions, and time to apply the patches. If you are doing things on a vsync cycle, you can always buy time by splitting up writing patch data across a few cycles before you need to play the first note. But here, we just want to initialize the OPM and get to writing our patches once and forget about them. These register value pairs at the top are what you want to do anytime you start using the chip, getting some basic settings initialized and silencing all the channels. Then we have the patches, starting with channel 1, where we set up the piano patch. I won't get into what all these settings do, but they end up kind of sounding like a piano. This patch comes with a chiptune tracker program called Deflamask, and we'll learn more about that later. After we write it to the channel 1 registers, we do the same for channels 2 and 3 and 4. When we get to channel 5, we start writing different values to those registers, as this is supposed to be a string voice that could stand in for a string ensemble when played with other string voices. This patch also came from DefleMask, and we apply that to channels 6 and 7 and 8 as well. Now let's take a look at the track data. This file uses the macros we defined earlier, and they all produce more register value pairs. The weight half beat will use our special weight register value and helps break up our 4/4 measures into 8 half beats. We then simply play the notes on their starting half beats, then switch to a different note when the next one is played, or put in a rest when that channel needs to go quiet. Each measure ends with its 8th weight half beat macro, and we keep going until measure 10 is complete. And then we put in an end music instantiation, which will make the program stop playing and return to basic. If you want, you can track out the rest of the score, which I have included in the repo under the Lesson 17 subdirectory, along with all this code. You may see that Mozart was fancy enough to do some 16th and grace notes, which we can't do with our current player that is fixed to a 15-tick cycle, so you have to sort of glaze over some of that. But while you're at it, you could have variable wait times by changing the wait macro to take a tick count, rather than always waiting 15 ticks, and change the track playback code in the RQ handler to use that. But for now, we're just going to build this code as it is. Of course, we have a build script for that. As you'll see, we only have to assemble music.asm, which we build into music.prg. The .include commands take care of bringing along all 4 of the other files, so we don't need to call them out in the build script. Let's go to the terminal and try to run this. All right, let's run build.sh, and we'll do a directory listing, and we'll see that music.prg is right there. So let's run the emulator, and we'll maximize that so we can see it better. Let's load music.prg and run it. So there's our whole track. Like I said, it would be a good exercise to try modifying the track. Besides making it longer, you could also try changing the patches, either fiddling with the configuration or just turning off some of the channels by changing the op control registers to be 0. That way you could listen to just the piano, or just the strings, or just a subset of the voices. Of course, this is a very manual process for creating YM2151 tracks. But you don't have to do this by hand. You can use DefleMask like I mentioned earlier. DefleMask lets you define chiptune tracks from multiple systems, including Sega arcade cabinets that use the YM2151. We can use that mode to create tracks for the X16, just leaving out the PCM voices and only populating the 8 OPM channels. As an example, I'm going to load the title music for my upcoming game, Cavi's Quest, which was written by my collaborator, Joshua J. Salazar. Here you can see at the top all the instruments he defined for this track, and then the track itself at the bottom, which will insert the patches every time a new instrument is specified for a channel. Let's take a listen right now. DefleMask lets you get instantaneous feedback on the sound of your track and its instruments. And the nice thing is it's free and open source and runs great on Windows and Linux. The really nice feature is that beyond the included instruments, you can fiddle with the patch settings in a nice GUI. And that shows you all the 4 functions and a little line chart to visualize the settings for each of them. The little piano keyboard at the bottom lets you hear how the patch sounds for different notes. And once your patch is how you like it, you can save it and then play your track immediately with a modified patch, even letting you isolate the channels it's going to be on. Once your track is complete, you can export it to the VGM format, which is what the XCI software development kit uses to import music into your game. Let's go see this track in action. Let's load xci.prg and run it. If you want to see how the SDK and game engine do this, I have a patron-exclusive video available on Patreon, which you can get access to by pledging as little as $1 a month. But I also have a lot more content available for free here on YouTube, including a whole series on XCI development and a few more episodes in this assembly series before it's done. If you don't want to miss any episodes in the future, make sure you subscribe to my channel and click the bell to get notified when they come out. If this episode taught you anything, please click the like button, and if you have any questions, please put them in the comments, and that can influence how future episodes are made. If you can't wait for the videos to go public, become a patron and get access to new videos as soon as possible, just like the folks you see here did on my Patreon page, which you will find linked in the description along with the GitHub repo containing all the materials for this tutorial series. Thanks for watching, and I hope to see you again soon. Bye-bye.